All right, so in organic chemistry, we have an extremely convenient convention that we use to convey lots of information with the least amount of details. So before I show this to you, this line bond structures, before I show it to you, let's appreciate why it's necessary. Look at this structure of amoxicillin. There is a lot going on here. This is just way too complicated, and it doesn't actually give us that much information. It actually sort of obscures the real point of the structure of amoxicillin. So if instead we draw it like this, watch this. If instead we draw it like this is the bond-line structure, or we might call line bond structure. We do use both those terms. Then you can see we have basically all the same information in it. We're assuming here with this picture that this is a carbon, that's a carbon, that's a carbon, that's a carbon, that's a carbon. We're assuming that this nitrogen is neutral, so it must have a lone pair here. This oxygen is neutral, so it must have two lone pairs here. Right? You see all the information that we need if you agree that all of the implicit atoms are going to be carbons, and every carbon is going to have 4 bonds, so there must be a hydrogen on there, right? So if we set a few ground rules at the beginning, we can agree that this structure down here is amoxicillin. It gives us just as much information, but it also keys our eyes into some of like the important features of this. Like there's a carbonyl carbon. Whoa, look at that. Looks just like an amino acid. There looks like an organic acid, right? And you can see that stuff a lot more easily if we don't have all these extra atoms in there that we can assume. Okay, so let's look at how to draw line bond structures. Okay, so the first thing we're going to do is we're going to start with the assumption that every corner or endpoint, every joint or terminus is a carbon atom. Okay, and so this is a carbon atom. Here's a carbon atom. Here's a carbon atom. Here's carbon, carbon, carbon. Okay. And we're going to also assume that the zigzag format is relatively accurate with respect to its bond angles. So the bond angles between a sp3 hybridized atom are about 109.5. Okay, and so we'll draw that maybe like that might be, I don't know, 110 degrees, right? We'll say that. And in sp2 hybridized carbons, it's 120 degrees. So maybe that's 120 degrees, right? But with sp hybridized, those are linear. And so we do draw the linears like this. Okay? So there are 6 carbon atoms here. There are 4 carbon atoms here. There's a double bond between these guys. And there are 4 carbon atoms here, right? So the carbon atoms are not labeled, and that helps us conserve a lot of ink for that, right? And doesn't clutter up our eyeballs for that. And also, every carbon atom has 4 bonds to it. And so if only one is drawn, then it must be that these remaining 4 are hydrogens. I mean, these remaining 3 are hydrogens. And this carbon's got 2 bonds to it, right? So it must be that the other 2 are hydrogens, okay? So that is the key for line bonds, all right? Now, you also have to be able to interpret the number and locations of the hydrogens in a molecule, which is what we were talking about just there. Hydrogens are not shown, but it's assumed that every carbon has 4 bonds. And so put the hydrogens in like I did in that previous slide. All right. Now we're given a line. If you're given a Lewis structure or a condensed structure, you need to also be able to draw it with its corresponding line structure. And here's how we're going to do it. We're going to say this carbon is here, and it's bonded to another carbon, right, which is here. It's carbon 2, so that'll be carbon 2, right, and it's bonded to a third carbon, right, third carbon, and a fourth carbon, right, and now we're going to say all the hydrogens are going to be implied, and so in fact that's it right there. That's rule number 1, is we're going to draw sp2 and sp3s, and we're going to draw them in a zigzag format, which is relatively, I don't know, 110, 120 degrees, right? We're just approximating it, right? We're trying to get something that helps our eyes sort of fit in our eyes as realistic, all right? So rule number 1 is draw sp2 and sp3 as zigzags. Rule number 2 is when we're drawing double bonds, you give some kind of representation that is going to be somewhat realistic, right? So if I draw a double bond, then I'm going to draw these other bonds coming off here like this, right? That's better than this because we know that these bond angles are about 120 degrees, right? These are all about 120 degrees, and so it wouldn't make any sense to draw it like this. It would draw it more like this. This is definitely going to get into your heads better over the next few weeks too, right? So you draw the SP2 hybridized systems like that, and then rule number 3: when you're drawing single bonds, the direction in which you draw those bonds is irrelevant. Why? Because they're just end to end, and so there's actually free rotation about every single bond. Okay, so since there's free rotation about that bond, it could be that this guy would be rotated up here like that, and it will be the same thing because this bond right here rotates freely. So rule number 1 is SP2, SP3 go zigzag. Rule 2 is we draw all the bonds as far apart as possible. Rule number 3 is that the single bonds, it doesn't matter which direction we draw them, right? So we draw them some way that's convenient for us. Rule number 4 is all heteroatoms, that is atoms that are not carbon and hydrogen, have to be drawn out. Okay? So that may seem like a lot, but it turns out most of the atoms we're drawing are carbons and hydrogens anyways. So we draw those out, and then any hydrogens that are attached to them also have to be drawn. Okay? And so, so this is the structure, right? You can see 1, 2, 3, 4. So I go 1, 2, 3, 4. And then on the second carbon, I've got an OH. So I draw it like that. Okay? And that's it. Now, I don't have to draw the Lewis dot structures. I oftentimes do the Lewis dots, the lone pairs. I oftentimes do draw those lone pairs because lone pairs on oxygens and nitrogens are frequently the center of the conversation. And it just takes an extra second to draw it. Not all line bond structures have those lone pairs. I think it's a good habit to get into. Rule number 5 is that you never draw 5 bonds to a carbon, or 6. It's always 4. Never draw more than 4 bonds to a carbon. Okay, so now let's do a couple examples. Let's draw some line bond structures for each of these guys here, okay? So what I'm going to do, first of all, is I'm going to find the longest carbon chain, and I'm going to find what things are connected to it, okay? So it looks like I've got a carbon. I'm going to have to make some notes to myself because this is going to be, these are pretty complicated molecules. That's these 2 guys right here, okay? I just draw those. And it looks like I've got 3 methyl groups coming off of each of them. Well, actually, that was simpler than I expected, right? You see my CH3s, there's my 3 CH3s. Remember that the end of a line is really just a carbon, and every carbon's got 4 bonds. So that's going to be a methyl group. That's going to be a CH3. So this really is more accurately drawn as, I'm going to draw this 1, 2, 3, 4, okay. 1, 2, 3, 4. It looks like on carbon 2, I've got 2 more methyl groups coming off. And on carbon 3, I've got 2 more methyl groups coming off. And the last thing I'm going to do is I'm going to go through and count everything and make sure I've got the right number of atoms. So looks like we've got 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. And I've got 3 here, plus 2, plus 3 more. There's 8 carbon atoms here. So this is correct. All right, let's do the same thing over here. So it looks over here like I've got 1, 2, wow, buckle my shoe, right? Let's draw this carbon first. I gotta make notes. This is complicated. Let's do this carbon here, okay? And it looks like it's got 3 ethyl groups coming off of it. So there's 1, there's 2, and there's a third one, right? That's those 3 ethyl groups there. And it looks like it also has a hydroxyl. Okay, so I think I can clean this up a little bit. That's not quite good enough because I've got a carbon in there, right? So you can't have that if it's a line bond. So what I'm going to do, so I'm going to say there's carbon 1, 2, 3. How do you spell 3? 3, 4, 5. See, I'm looking for a long continuous carbon chain. 1, 2, 3, 4, 5. That's a long continuous carbon chain. I'm going to go back to red, I guess. 1, 2, 3, 4, 5, right? So I've just drawn that one, that one, that one, that one, and that one. Now it looks like on carbon 3, I have another ethyl group. So I could do that. And it looks like I also have a hydroxyl. So I'm going to stretch that out a little bit there. And last thing I'm going to do is count all my atoms to make sure I've got the right number. I've got 1, 2, 3, 4, 5, 6, 7 carbon atoms. And it looks like 2 times 3. There's my 6 there. There's my 7th, right? 7 total. And an OH. So yeah, this is it. This is a legit structure. That's my line bond structure for that. So you can see this is going to take some kind of a systematic approach. It's really more like an accounting game, right? Where you go through and make sure you've got everything. And you follow the rules of every carbon's got 4 bonds. Every bond that's not shown on carbon is a hydrogen. And all heteroatoms are drawn out with their hydrogens. And you should be good. All right, good luck.